Section: Introduction. In this section, we have introduced the challenges faced by the Adam optimizer in training large language models, LLMs. Although Adam is known for its high performance, it comes with a significant memory cost due to the storage requirements for its optimizer states. This memory overhead poses a major obstacle in LLM training, especially when dealing with massive models like PaLM with 540 billion parameters. To address this issue, we aim to develop a more memory-efficient optimizer that could alleviate the burden on CPU offloading, reduce the need for parameter sharding, and enhance the overall training process by minimizing communication between GPUs and CPUs. Our goal was to enable training LLMs with fewer GPUs, leading to cost and energy savings, as well as making LLM training more accessible to researchers with limited GPU resources. One of the main challenges in modifying Adam is the lack of understanding regarding the roles of its first-order and second-order momentum terms. Previous attempts to reduce memory usage, such as Adafactor, have not been successful for training large language models, indicating the complexity of the optimization process. In our work, we proposed a novel approach called AdamMini, which significantly reduces the memory footprint of Adam by simplifying the learning rate assignment process. By partitioning the model parameters based on the structure of the transformer's Hessian matrix, we were able to assign a single learning rate to each block, leading to substantial memory savings without compromising performance. The key advantages of AdamMini include its lightweight design, effectiveness in maintaining or even improving performance compared to Adam, and efficiency in terms of throughput and training time. By focusing on the partitioning principle and leveraging the Hessian structure of transformers, we were able to develop a more efficient optimizer that can benefit a wide range of tasks beyond LLM training. Section Summary. In this section, we introduce the challenges posed by the high memory consumption of the Adam optimizer in training large language models, LLMs. We propose a new optimizer called AdamMini, which significantly reduces the memory usage of Adam by partitioning model parameters based on the Hessian structure and assigning a single learning rate for each block. AdamMini demonstrates comparable or improved performance to AdamW across various LLMs and other tasks, achieving higher throughput and efficiency without introducing extra compute in per-step updates. Section: Method. In this section, we will discuss our observations that inspired the creation of AdamMini. We began by examining the role of a key component in Adam, denoted as number 20, which assigns a specific learning rate to each parameter. This individualized learning rate allocation is crucial for transformers as different blocks require varying learning rates. This necessity arises from the fact that the Hessian matrices of transformers and neural networks exhibit a near-block diagonal structure, indicating the need for diverse learning rates across blocks. Additionally, each block in transformers displays a significantly different distribution of eigenvalues, further emphasizing the importance of tailored learning rates for optimal performance. While it is established that distinct learning rates are essential for each block, Adam goes a step further by assigning a unique learning rate to every parameter, considering the vast number of parameters compared to the relatively fewer blocks. To investigate the effectiveness of multiple learning rates, we conducted experiments on optimization problems, specifically focusing on a random quadratic minimization problem with a block diagonal Hessian matrix. The results revealed that Adam, with its parameter-specific learning rates, outperformed traditional single learning rate methods. However, for certain dense subblocks within the problem, a single optimal learning rate proved to be more efficient than the multitude of learning rates assigned by Adam. This phenomenon suggests that for problems with block diagonal Hessian structures, employing numerous learning rates may not always yield superior results. In fact, a single well-chosen learning rate for dense subblocks can outperform a complex multi-rate approach. This observation hints at the limitations of Adam as a preconditioner for reducing the condition number of dense submatrices. Similar trends were observed in transformers, where a simplified learning rate strategy could match or surpass the performance of Adam with significantly fewer rates. To address these findings, we introduce AdamMini, a streamlined variant of Adam aimed at achieving comparable or enhanced performance with a drastic reduction in the number of learning rates required. The design of Adam Mini involves partitioning model parameters into blocks, with a specific focus on the EMB_ block for transformers. By utilizing a simplified learning rate selection process based on mean values, Adam Mini streamlines the learning rate assignment process while maintaining performance levels. Section Summary. In this section, we investigate the observations that led to the development of Adam Mini. By exploring Adam's individual learning rates for each parameter, we discovered that transformers require varying learning rates for different blocks due to their block diagonal Hessian and eigenvalue heterogeneity. Our experiments revealed that for generic problems with block diagonal Hessians, using fewer learning rates can sometimes outperform Adam, leading us to propose Adam Mini as a more efficient alternative with significantly fewer learning rates. Section. Principle for the partition strategy. In this section, we discuss how we choose the parameter partition for Adam Mini. We have a general principle, as shown in Principle 1, based on the analysis in the previous section. We use this principle to come up with a partitioning strategy specifically for neural networks. We start with the default partition in PyTorch, which is based on a block diagonal structure commonly seen in the literature. This default partition works well for non-transformer tasks like ResNet, diffusion models, and graph models, which we refer to as partition for non-transformers. However, we discovered that this default partition doesn't always work effectively for transformers. In particular, we noticed training instability with Adam Mini on 1B models. Upon further investigation, we found that the default PyTorch partition didn't fully capture the Hessian structure, especially for transformers. By examining the Hessian of a 4-layer transformer, we identified two classes of Hessian subblocks. Class 1 includes query and key, which have a block diagonal structure with smaller dense matrices, while Class 2 consists of dense structures like value, attention projection, and MLP layers. Based on our findings, we realized that the default PyTorch partition isn't the best fit for transformers. We observed that queries and keys could be partitioned into different blocks by head, as different heads in transformers play distinct roles in understanding tokens and may require different learning rates. Following this insight, we introduced the partition for transformers strategy, which partitions queries and keys by heads, aligning with the smallest Hessian subblocks. This strategy has proven to stabilize training and enhance performance. Moving on to some characteristics of Adam Mini, we note that it reduces memory usage significantly for transformers by reducing the number of learning rates. This reduction in memory depends on the fraction of non-embedding parameters in the model. Additionally, Adam Mini achieves higher throughput compared to AdamW, especially with limited hardware resources, due to reduced communication overhead and minimal extra computation in its update rules. Furthermore, Adam Mini does not conduct matrix factorization, which is costly and often present in low-rank approximation-based optimizers. This design choice allows Adam Mini to achieve faster per-step updates and reduce the overall time required for pre-training. In our experiments, we observed a substantial increase in throughput with Adam Mini compared to AdamW when pre-training Llama 2 to 7B on GPUs. While the current design of Adam Mini may not be optimal in terms of learning rate design for each dense Hessian subblock, it still performs as well as or slightly better than Adam with significantly less memory usage. There is potential for further improvement in the learning rate design, which we consider an important direction for future research. Section Summary. In this section, we introduce a principle for choosing the parameter partition for Adam Mini, focusing on neural networks. We find that the default PyTorch partition works well for non-transformer tasks but encounters training instability on transformers due to not fully capturing the Hessian structure. By partitioning queries and keys by heads, following the principle based on the smallest Hessian subblocks, we introduce the partition for transformers strategy, which stabilizes training and improves performance by assigning different learning rates to different heads. Section. Experiments. In this section, we will test the effectiveness of AdamW. Our main focus is on tasks related to large language models, LLMs, such as pre-training, supervised fine-tuning, SFT, and reinforcement learning from human feedback, RLHF. We will also assess AdamW's performance on tasks not related to LLMs. All experiments involving LLMs are carried out using 4 NVIDIA A800-80GB GPUs, while the rest of the tasks are done using 4 V100 GPUs. Detailed information about all experiments can be found in the appendix. Pre-training. We start by pre-training various open-source LLMs, including the GPT-2 series and Llama series, from scratch using mainstream English corpus. For instance, we train the GPT-2 series on OpenWebText and the TINYLLAMA1B, Llama 2-7B on Common Crawl. Different model configurations, such as context length, are chosen based on standard protocols. We compare AdamW with AdamW and other memory-efficient methods like Adafactor, CAME, and SM3. To ensure a fair comparison, momentum is incorporated with a specific value for Adafactor and SM3. The learning rate for all methods is fine-tuned within the same budget, and the best performance is reported. Llama series. Our experiments show that AdamW performs similarly to AdamW but with lower memory usage for both tiny Llama 1B and Llama 2-7B models. GPT-2 series. AdamW demonstrates comparable performance to AdamW with less memory consumption for various GPT-2 models. However, a specific configuration called AdamW, all-packed, does not perform well and shows unstable behavior. Sensitivity analysis. We conduct sensitivity analysis on the GPT-2-125M pre-training task and find that AdamW is not highly sensitive to hyperparameters. Supervised fine-tuning and RLHF. We evaluate AdamW's effectiveness in downstream fine-tuning tasks, including supervised fine-tuning and reinforcement learning from human feedback. Our results show that AdamW outperforms AdamW in terms of chatability, even though it uses a single learning rate and is more memory efficient. Non-LLM tasks. AdamW is also evaluated on non-LLM tasks like training ResNet 18 on IMOGNet, diffusion model on Celeba, and Graph Convolution Net, GCN, Graph Attention Net, GAT, on OGB Archive. The results indicate that AdamW achieves comparable or better performance than AdamW with lower memory usage. Related works. We discuss the effectiveness of Adam and various lightweight optimizers for general tasks, highlighting the performance of AdamW compared to other methods in different experiments. Section Summary. In this section, we verify the efficacy of AdamW by focusing on language model, LLM, tasks such as pre-training, supervised fine-tuning, and reinforcement learning from human feedback. We conduct experiments on various LLM models like GPT-2 and Llama series, comparing AdamW with other memory-efficient methods like Adafactor and SM3. Our results show that AdamW performs comparably to AdamW with reduced memory usage across different tasks, including non-LLM tasks like training ResNet 18 and Graph Convolution Net. Section. Concluding remarks. In this section, we introduced AdamW, a more memory-efficient optimizer compared to Adam, saving around 45% to 50% of memory. One drawback is that AdamW does not address Adam's heavy overhead. We think there is potential to simplify this overhead in the future.